All right. Well, thank you all for coming to this seminar. And for those of you who are not in California, thank you for accommodating your time. I know some of you probably live in other countries where the time is inconvenient, so thank you for doing that. Just know that we will be recording this, so we have the video for you, but it's going to take a little bit of time before we post the video. So it's good that you're here today. So my name is Johnny Lin. I am a consultant at the IDRI Statistical Consulting Group at UCLA. Here with me today is Andy Lin, my supervisor, and Siavash Jalal. So they will be monitoring the chat today. So if you have any questions, just send them to the chat. Mostly they'll be monitoring it, and then sometimes I'll check in to see if there's any questions too. But if you have questions, just ask Andy or Siavash directly, and then, or you can unmute your mic and just ask me directly. My name is Johnny Lin. All right, so if you haven't done so, please go to the webpage. The webpage is listed here. I think I also pasted it into the chat. The easier way to go to the webpage is also to go to our homepage. I'm sure you've seen it before. And just go to upcoming events, click on Introduction to SEM, and then access the seminar link here. Okay, so you should all be on this page. So before we get started, I would like to have some of you participate in a background poll, if that's okay. You don't have to respond, and it's completely anonymous, but I just kind of want to get a sense of your background, okay? How familiar you are with the things I'm going to talk about today. So for example, how familiar are you with R? How about, have you used the LM function before? Have you taken a previous course in factor analysis, CFA? Have you used Lavaan? And how comfortable are you with matrix notation? Right? Have you seen matrices? Do you know what the dimension of a matrix is, like the rows and the columns? Do you know what a vector is? Do you know what matrix addition and multiplication are? If not, it's okay. I just want to get a sense of your background. Okay, I see some of you answering already. A lot of you are answering, great. All right, so I'm going to close the poll in 5 seconds. 5, 4, 3, 2, and 1. Okay, so it looks like you guys are pretty familiar with R. That's good. And, oh, you use LM. Okay, so you know linear regression. That's great. Okay, so you haven't taken a course in CFA, but know a little bit about it. You've never used Lavaan. Okay, that's great. Okay, that's really good to know. And you know a little bit of matrix algebra. You're not afraid of it. That's perfect. Okay, that's great. I really thank you for filling that out. That's actually really helpful. All right, so since you guys know regression, I can kind of zoom past it a little bit. So this is Introduction to Structural Equation Modeling in R with Lavaan. So if you never heard of structural equation model, it's basically a larger umbrella of linear regression or linear models in general. So SEM or structural equation modeling encompasses both linear regression. It also encompasses multivariate regression, path analysis, CFA, and structural regression. So if you've never heard of some of these terms, we're going to go through them so you will be familiar with them by the end of the seminar. This seminar is going to cover some matrix notation. So if you have never taken a course in linear algebra, that's okay, because you don't really need it to understand most of the seminar. It does help, though, in understanding the fundamental technical aspects of SEM, because SEM by nature is a matrix kind of model, okay? We're going to go over topics such as identification in CFA, just very briefly. Like, what does it mean to be identified, over-identified, under-identified, for example? And we'll go over model fit, for example. Okay, so those are some of the topics we're going to go over. we're not going to cover more advanced topics like multiple group SCM, measurement and variance. You may have heard of these if you've taken a course in CFA, latent growth modeling. So these are topics that we may explore in a future seminar. Okay, if you're interested, this is a great time to think about what future topics you want, and you can fill out your comments in the feedback survey that we're going to provide at the end of the seminar. So I assume that you saw my email, and if you have, I recommended you to kind of look at this page, confirmatory factor analysis in R with Lavaan, because some of the material does overlap. Okay, so if you've seen this material, the CFA part will be pretty straightforward. I also asked you to kind of review matrix notation, and that's going to be helpful for some of the rest of the seminar. So I'll just go over kind of what we're outlining today. And everything you see as an underline here is going to take you to a section in the page. So you don't have to keep like scrolling up and down. So when I click introduction, it should lead you to the introduction. And then if you want to go back to that outline, you just click back on your browser. I'm using Firefox. You can use Edge or Chrome or Safari. It's the same thing. So we're going to talk about just generally what is structural equation modeling in terms of a motivating example. So I kind of like, having real world examples. We're going to talk about a fake real world example, but it's going to be real data, okay, not just abstract matrices. We're going to go over some basic definitions that you'll need to know before you move on to all the models. We're going to talk about what a path diagram is, and then also a quick reference of Lavaan syntax. Since most of you haven't even heard of Lavaan, it's good to kind of know how to specify Lavaan syntax. And then we'll talk about all the models. Okay, so SEM, remember, is an umbrella term for a lot of models. So like I said, simple regression and multiple regression, these are actually under the umbrella of SEM. So we're going to just go over that really briefly because you already know what that is. But just how Lavaan, for example, specifies a regression model. And then maybe these models you haven't heard of, but there's multivariate regression. Okay, and then we're going to talk about multivariate regression. We're going to talk about degrees of freedom, path analysis, and a modification index, okay, what that is. Then we'll talk about model fit, okay? How do you assess the quality of your model? The main thing you want to know is the model chi-square, okay? That's going to pop up a lot, the chi-square statistic. If you've done like, chi-squared goodness of fit test, it's kind of like that. And then we'll talk about, the types of model fit, like the CFI, the TLI, RMSEA. If you've taken CFA, you've probably heard of these models. And then we'll talk briefly about CFA models, or measurement models, what an exogenous factor is, what an endogenous factor is. This is going to be a review of the CFA seminar. And then finally, we're going to talk about structural models. This is probably new to you, and structural regression, what is that? Okay, so yeah, there's no video because this is before we recorded, but the seminar notes are available to you, and then if I happen to do one in the future, I'll record it. Okay, but yeah, yep, and then that's it, and then we'll conclude with kind of a summary of all the models we discussed. Okay, any questions about the topics we're going to cover today? So by the end of the seminar, you should be able to identify which model is which, okay? So if I give you an equation or a path diagram, you can say, oh, that's a path analysis. Oh, that's a CFA model. You should be able to do that by the end of the seminar. And you should be able to actually run this in Lavaan, okay? So that's the goal of the seminar, the learning objectives. It's not a overarching broad like class on SEM, so don't expect that because there's so many topics in SEM that we just don't have time to cover. Okay, so this isn't going to be an interactive seminar, like I said, but it is good to just practice installing a package like Lavaan into R and then loading the library. And if you weren't here when I discussed this is the full code that we'll be talking about, scm.r. And if you copy and paste this into R or RStudio, you should be able to run all of this code yourself. So it's good to kind of follow along if you have time. If not, then it's okay. All right, any questions before we start the content? You can always unmute your mic and just remute it later. And then also you can put your questions into the chat. Okay, so let me just make sure. I want to see myself. Okay. So we're going to talk about SEM. Like I said before, SEM is a broad umbrella of models, okay? Linear regression, multivariate regression, path analysis, confirmatory factor analysis, structural regression. These are all things that fall under SEM. The important thing to note is, what type of variable you're talking about. You've probably seen observed to observed variable relationships. This is basically regression. Observed means things you actually have data for. Now, confirmatory factor analysis models the relationship of latent variables to observed. These are unobserved variables, okay? So bridging that gap between unobserved and observed variables. And then finally, structural regression relates latent to latent variables. So unobserved to unobserved variables. That's probably something you haven't seen before if you haven't taken SEM. SEM uniquely encompasses both the measurement and the structural, okay? The measurement, which is the CFA, and the structural regression, meaning the regression paths. So that's the unique contribution of what SEM provides over and above other models. And so basically, we're going to go over for every model, the matrix formulation. Okay. We're going to go over the path diagram, the Lavande syntax, and the interpretation of the output and the parameters. Okay. Now let's talk about the motivating example, which I kind of like. I like talking about real world things, even though this is not a real data set. Okay, so we've had people assume these were real data sets and like generalize too much out of it. Just treat it like it's like a fake data set. Okay, it's just as an example to show you how Lavande works. But in this fake data set, you are a researcher studying the effects of student background on academic achievement. Okay, so your lab has finished collecting and uploading the data set. So you can download that data set actually right here as a comma separated file, or you can load it directly into R, like I showed you above. So this data set consists of 500 students with 9 observed variables: motivation, harmony, stability, negative parental psychology, SES, verbal IQ, reading, arithmetic, and spelling. You'll get used to these variables as we go through the seminar. Now, the principal investigator hypothesized 3 latent constructs: adjustment, risk, and achievement. So these are not observed in your data. That's what I said before. This is latent, okay? So adjustment is measured by motivation, harmony, and stability. So how much a student seeks harmony in their relationships with their classmates, that's going to be an indicator of their adjustment to the classroom. Risk, if, for example, it's like negative parental psychology, SES, verbal IQ. So the more negative the parent's psychology towards the student, probably the worse the student is going to do, right? The lower the SES, the more likely the student is going to not do well. Okay, so these are risk factors, for example. And then finally, the achievement variables. So these are just academic achievement scores: reading, arithmetic, and spelling. So this is basically kind of the variables, the data sets that you'll be working with today. Now, there are many packages in that do SEM, but R is free, so that's always good. And then Lavande is pretty simple to use. It does have limitations, which I won't really discuss today, but it's relatively easy to use. And that's why I kind of want to go over the technical details a little bit, because it's so easy to use that you miss kind of what SEM really is. Okay, so if you want to load the data set directly into R, you can use this command right here. Okay, so that just calls the read.csv function, and the contents are the website itself. Okay, so this is where we get into a little bit of a technical detail. The most essential component of an SEM is the covariance, okay? Or you can think of it as the relationship between items. If you've heard of correlation, a correlation is basically a standardized covariance, okay? Now this is a little technical, so bear with me. This is where we also get into a little matrix notation. So the true population covariance is called sigma, okay? And this is called a variance covariance matrix. Why is that? Because we have variances on the diagonals. So when you see a diagonal, I just mean the entries here. If you draw a diagonal line through the matrix, okay? And a covariance of a variable with itself, like motivation with itself, is the variance, okay? Now the off diagonals, the things that are not down this diagonal line, are the covariances. So 77 is the covariance between harm and motivation. It's positively associated. So as harm increases, motivation, harmony means harmony. So harmony increases, motivation increases. Now look at parental psychology. As negative parental psychology increases, student motivation goes down. Okay, right? So if your mom is like yelling at you all the time, the student's probably not going to be doing their homework as willingly. So that's what you need to know about the variance covariance matrix. You also note that this is a square matrix, right? So the total number of rows equal to the total number of columns. You'll also notice that things on the upper diagonal, meaning the things that are above this diagonal line, are the same as the things in the lower diagonal, the things below that diagonal line. So the relationship covariance between harmony and motivation is 77, which is the same as the covariance of harmony and harmony and motivation. So harmony and motivation is the same as motivation and harmony. So it's basically symmetric. All right, so that's important to note, because once we know the lower diagonal, we don't need to know the upper diagonal. All right, so in the population, this is called sigma, right? The variance covariance matrix. But what we have here is not sigma. Why? Because we don't know the population, right? So we don't know what the true population variance covariance matrix is. What we have here in the data is a sample of the population. So this is basically an estimate of the population covariance matrix, and that's called sigma hat, or S. So this matrix that we're getting out of the COV function, because we're looking at the data itself, is S, okay? Or the sample covariance matrix, variance covariance matrix. The final thing you have to note is what is a model implied covariance matrix? Right here. Okay, so a model implied covariance matrix is called sigma theta. What is theta? Theta are basically parameters. So a regression path, like a coefficient, okay, or a loading in factor analysis. I'll talk about that later. But you're assuming that you can recreate this population sigma using the parameters. So that's called the model implied covariance matrix. The purpose of SEM is to reproduce the variance covariance matrix using parameters. Okay, and then if it perfectly produces the variance covariance matrix, then sigma should equal sigma theta. Okay, so to test your understanding, I'm going to do another poll. And don't worry if you don't get everything correct. I just want to see if you're kind of following what I'm saying, if that's okay. And basically, you don't have to get it right or wrong. Just kind of answer to the best of your ability, and I'll see if I should be talking less about technical or more, depending on if you understand what I'm saying. So that was a little bit more technical. And based on your feedback, I'm going to see if I should talk at this level or just kind of make it more accessible. Oh, also the answers are there, so try not to peek at the answers. I just want to get a sense of if you can answer this yourself. Okay, great. Okay. I'll give you about 10 more seconds. It looks like you guys are. Don't worry if you don't get, and it's completely anonymous again. So I'm going to close this the survey in 5, 4, 3, 2, and 1. All right. So it looks like you guys are understanding what I'm saying, which is good. So running the cove command in R gets us the sample covariance, right? Not the population. So that's great. S means that we're estimating the population, the covariance. Yes. And then sigma theta is the variance covariance matrix reduced from model parameters. Perfect. Oh, great. Okay, so you guys are understanding what I'm saying, and that's great. I love that. So that means I can go a little bit more technical. Perfect. Okay, so before we proceed with all the models, I wanted you to go over some of the basic definitions of that you'll encounter in any kind of like structural equation model or latent variable model. You know what observed variables are. Okay, so they're variables that exist in the data. So the things that we had above, harmony, stability, those were all observed variables. Maybe you've heard of them called items too, if you do surveys, or manifest variables. Okay, these are all kind of the same words for the same thing. Latent variable, like I said, is a variable that's constructed and does not exist in the data. It's hypothesized. Okay, so this might be new to you. This comes from econometrics, but basically, what's the difference between exogenous and endogenous variables? Well, in SEM at least, an exogenous variable that is a variable that is, it can be either observed or latent. And if it's observed, it's called X. If it's latent, it's called, this is Kasi. It's the Greek, it's Greek. So just know that we'll have a lot of Greek letters today. And that explains an endogenous variable. So it's basically like a predictor in regression, right? It explains an outcome. Endogenous means a variable that is being explained. So you've heard of like the DV, dependent variable. That's kind of what an endogenous variable is. It can be observed or latent though. Maybe that's new to you. A measurement model is a model that links observed with latent variables. Okay, so if you have a mix of observed and latent variables, that should be under a measurement model. And that's, for example, a CFA, a factor analysis. An indicator is an observed variable that resides in a measurement model. So if you're talking about observed variables in a measurement model, these are indicators of the factor. And the factor is the latent variable defined by the indicators. So all of these, though, can be endogenous and exogenous. A loading is a path between an indicator and a factor. So we've talked about measurement models. Now we talk about structural models. And structural model is a model that specifies causal relationships among exogenous to endogenous variables. You can actually have endogenous predicting endogenous, which we'll see later, but it's basically kind of the regressions. Okay, so think of regression when you think of structural. An regression path is a path between exogenous and endogenous variables that reside in a structural model. I didn't put that in, but it's basically, it has to be in a structural model. Now, this is just a note of technicality, but there's subtlety to the definition of exogenous and endogenous. Okay, so that's why we don't really call it like independent or dependent in this seminar. So exogenous variables can be thought of as independent variables, right? And endogenous variables can be thought of as dependent variables. That's usually what you see before in regression. But in a measurement model, an indicator variable that is kind of predicted by an endogenous factor can itself be an endogenous. So basically, if a variable is predicted by an exogenous factor, it's exogenous. If a variable is predicted by an endogenous factor, it is endogenous. Okay, so I won't go over the true or false here because it's a little just technicality. But we'll, if that didn't make sense to you, we're going to explain that a little later too. All right, this is where kind of the fun part comes in because I like path diagrams. I like visuals. So I like matrices, but I like figures even more. That's why path diagrams were developed because, you know, SEM is a matrix kind of model, right? So sometimes it's hard to kind of just see the matrix. It's easier to just see like circles and squares, okay? So you just have to know what these mean. So a circle is a latent variable. It's like a factor, right? Like adjustment and risk, you know, those were the variables. Circles don't exist in the data. Squares, observe variables do exist in the data. So if you see a square, it means that you can find it in the R data set. A triangle is the intercept. We don't really talk about intercepts here, but you will be just referencing some of that. The most important thing is these arrows, right? So a single arrow is a path, so like a regression path, and a double arrow is either a variance or covariance. Okay, so here's an example. So like, what's this circle predicting a square? That means it's a latent variable predicting an observed variable. This, in a measurement model, this would be called an indicator, and this would be called a factor. Now, what is a square? This square is a latent variable. What is this double arrow? This is the variance of the latent variable. Okay, so that's how you read the path diagram. It's not too hard to read. That's why people draw it, because it's so intuitive. Okay, so this is going to be the big kicker. You have a lot of things going on, and just I want to just say something before is this all falls under SEM, but okay, this is not like every program has this kind of terminology. This is what we call list roll. And if you haven't heard of list roll, it was invented in 1976 by Carl Jørgenskog. It stands for linear relations or structural relations. And basically, he invented SEM, okay, in 1976. So SEM is a relatively new field, even though 76 sounds like a long time ago. But it's relatively new in statistics. And this is his original formulation of SEM. Now, I'll just tell you up front is that Lavande does not use list roll notation, okay? Lavande does not use list roll notation, but I teach it in list roll because list roll is the foundation of Lavande, okay? So bear with me if this seems like a lot of terms to memorize. You won't need to know all these terms when you run Lavande, okay? But knowing these terms will help you understand SEM, and that's why I'm going over it. So the first thing I want you to really look at is the left-hand side. Okay, like I said, measurement models relate latent variables to observed variables, okay? Now, this is called a latent exogenous variable, okay? Why is that? Because you see that it's predicting something else. It's predicting an endogenous latent variable. Now, first we want to establish the measurement model, okay? So to establish a measurement model, because a latent variable can't exist on its own. It has to exist as a product, as a function of its indicators, right? So this is like motivation, harmony, and stability, for example. These are all observed, right? And then adjustment is the latent variable. So a relationship between a latent variable and an indicator is called a loading. It's like a regression path just in that special case. Now, if you see here, these indicators are being predicted by something, which means they have a residual, right? These residuals are also latent variables because they're not observed. And then the double arrow means they're residual variances, okay? So you have the exogenous latent variable predicting the exogenous indicators through the loadings. Then you have the residual variances of the indicators. The double arrow on this exogenous latent variable means this is a variance. So that's the exogenous variance. Now, the structural path links latent variables to latent variables. So you have an exogenous latent variable predicting an endogenous latent variable. Well, a latent variable doesn't exist on its own. It has to be a function of its indicators. Now, these indicators are a separate type of indicator. These are called Y indicators. The indicators we talked about before are called X indicators. Okay. Oops, what did I just do? So that works too, I guess. So you have basically two types of indicators, one that's exogenous and one that's endogenous. Now, the indicators itself have residual variances and residuals, right? But what is the difference between the endogenous latent variable and the exogenous latent variable? Well, because it's being predicted by an exogenous variable, the latent variable itself has a residual, and therefore it has residual variance. I know this is a lot, so let me know if anything doesn't make sense at this point. And if we proceed through the seminar, we're going to go over this in detail, but this is just a really broad overview of what we're going to, or what SEM is basically. If you know this and you understand this, this is SEM. The important thing to note is also the difference between a measurement model and a measurement model and a structural model. Okay. Again, measurement models link latent to observed variables, and then structural models link latent to latent. Any questions about this path diagram? No? It's a lot.
Hi, Johnny?
Yes.
Thanks. I'm still struggling a little bit with why there is a separate residual variance for the endogenous variable. Like, would you be able to detect that in like mathematically, or is it just like a theoretical thing?
Yeah, there is definitely a mathematical formulation, which I'll cover later. But basically, just think of regression, right? So if you have regression, the outcome always has a residual. So y equals, beta 0 plus beta 1 x plus epsilon, right? The epsilon is a residual. So think of this as basically another regression. And what's the regression of? It's of two latent variables. That just treats this variable, let's say it's achievement, as a y, like a dependent variable. And that's why it has a residual variance. If that doesn't make sense, let me get to the measurement model and then it'll make sense, I promise.
Okay, thank you.
Yep. Any other questions?
Yeah, Johnny, does the y side measurement, does that variable always have to be latent? Or can it, I think I asked Andy this as well, but I just wanted to confirm that is structural equation modeling only for latent variables on that side, or can it be an observed indicator?
That's a great question. Yeah. Yeah. So what I'm showing you is more like a structural regression, which is what we'll cover at the end of the seminar. But basically, you can have indicators, outcomes that are square, right? If you have outcomes and exogenous variables that are square, you don't need the measurement model. Okay. And then you just have the structural model. So this is basically a structural relationship. Okay. The only reason we have the measurement model is because we want to link latent variables to each other. And that's why we have both the X measurement and the Y measurement. Does that make sense?
Yes, thank you.
Okay, great. Good questions. You guys have any other questions? And actually, it's great that you're unmuting. That's actually really good for me to address your questions directly.
Yeah. Book recommendations for introductory.
Well, introductory are like what we're talking about. Okay, introductory, I recommend Klein. So you'll see the references in the bottom of the page. but it's called Principles of and Practice of Structural Equation Modeling. That's less matrixy type introduction. Yeah, and then, oh, did you want to draw something? But basically, the other reference is the Joris-Cog reference. And I put the two references at the bottom. And that's basically what I'm covering today is the Joris-Cog reference with a little bit of Klein. Okay.
I just
Other
have one question.
Yes.
Yeah.
Of course.
Could you scroll back up to that so I could see
Yes.
the figure? Thank you so much. So you said that the exogenous indicators are the stuff that we measured, like motivation and harmony, and then the latent constructs that we were interested in. Could you just show me where those go?
You mean
where those would be?
Oh, the
If we were to apply your motivating example to this,
Yes.
like where would
Oh.
it go?
Yeah, so this is like motivation, harmony, and then stability. And then this is adjustment. Okay, that doesn't exist, right? It's latent.
Right.
And then this is achievement. And what is an achievement? It's spelling, reading, and math. Yeah, does that make sense?
Awesome, thank you.
Yeah. Any other questions? Those are good questions.
Yes, I have a question.
Of course.
So if the endogenous Latin variable is not existed, what if the from y side it is observed variable, while for the x side is an exogenous Latin variable. So we don't need a y side measurement model either, right? But previously you drew two squares, one for the x side, another one for the y side.
Yes.
If it is like we have the exogenous Latin variable from the x side, while for the y side it is observed variable. Do we still need the measurement model?
That is a great question. Actually, it's one of the things I wanted to cover today, if we have time, is technically you cannot do this if it's not a measurement model, right? Like this is structural. You cannot do this in literal. Okay, but I'll show you a trick if we have time, is that basically what it does is it does this. Okay, and this is the structural model. And guess what this is? This is the measurement. So it's a measurement model with a single indicator. So that's how it links the two together. But that's a good question.
Thank you.
Yeah. Any other questions? These are all good questions. Okay. Great. All right, so since most of you haven't even heard of Lavaan, basically Lavaan is a free version of SCM. And since SCM can do linear regression, you can do regressions in Lavaan, right? So for example, the tilde is basically like you use LM. You've used LM before. So that's like, you know, the Y and the X, right? So I see that here. So this is your dependent variable. This is your independent variable, endogenous, exogenous, right? This is probably new to you. This equal tilde, that basically says we are in a measurement model. Okay, so the left-hand side of this is the factor, and the right-hand side of this are the indicators. So it's kind of like opposite of what you expect, right? So this is like motivation. This is like harmony, stability, right? Then this is like adjustment.
Station going on. It would be great if we could have the Slack upgrades, which are allegedly coming, but they've been allegedly coming since September, because then you can.
Do you have a question, Nancy? Okay. All right. So, all right. So, and then the double tilde is the covariance. Okay. Now, you probably heard this before, but basically, what is the covariance of X on X? The covariance of X on X is the variance, right? Like I said before. Now, you can also have Y and X, and that's basically the covariance. All right, the tilde one that says I want the intercept. Okay, so this is saying I want the intercept of X. These you don't really use today, but it's useful for CFA. 1 star fixes the parameter at 1. So if you want the loading to be 1, this is what you do. NA frees the parameter. So if you want the loading not to be 1 and you want it to be free, then you say NA. And then this is A star labels the path. So we won't be using this as much. We won't be using these. We really will be using these. Okay, so focus on those. And all right. So that's basically an introduction to just things you need to know before we start talking about all the models. And here's where we get to all the models. Okay. I like starting with things we know, and that's simple regression. I'm going to go over it really quickly so that, because I know you guys know regression. So simple regression models the relationship of an exogenous variable to an endogenous variable, but that's observed. Okay, so that's the key, is the observation is necessary. You need to know that y and x observe in your data. And you've seen this equation before, beta 0 plus beta 1x plus epsilon. Now, maybe you haven't seen this notation because this is the notation that Yorskog invented. But the reason why he did this is because you're going to be using these Greek letters again and again. So the intercept is here called alpha. The regression coefficient is now called gamma. And then this is called zeta. Just think of like Z, zeta. This is G, gamma, okay? Alpha, A, just think of it like that. Don't think of it as Greek, because Greek kind of is intimidating. The important thing also that's not shown is phi. This is called phi. This is the variance or covariance of the exogenous variable. And psi, this is the variance covariance of the endogenous variable, okay? So these are all just things we have to note. Okay, let's see. Let's skip the poll for this one since you guys know simple regression. This is the fun part. This is the path diagram, okay? Remember I said the square is observed, right? So all these are square, right? What's not observed? The residual. The residual is unobserved here, okay? So basically, the exogenous variable predicting an endogenous variable. These are observed, right? So let's say this is motivation predicting reading, okay? That's what I have here. And then this means it's the intercept, right? The intercept is alpha, right? Now motivation has a covariance or variance. Read has a variance too, right? But it's not the read itself, it's the residual of read that has the variance, right? So here we're talking about a residual variance, not a variance of the variable itself. So that's key to know. So all these things can be specified in LM, right? So you have reading as your outcome, and then predicted by motivation. You've seen this syntax before. And then you run the summary, and then you get this table. The intercept is 0, okay? It's basically, okay? This means 0. Each is something, small number is 0. So why is it 0? Well, basically because everything is 0 or centered in this data set. So you're going to have intercept be 0. Now, what does this mean? This e to the negative 1 means 0.5. Okay, so it's 0.53. So for 1 unit increase in motivation, the outcome read increases by 0.53 points. So you guys know how to interpret regression coefficients. Now, maybe what you haven't seen before is how to do this in Lavaan, right? You remember regression is a special case of SEM. So that means you can definitely do it in Lavaan. Remember, the tilde is still the prediction, right? Now, why do I add a 1? Well, by default, Lavaan does not estimate intercepts, okay? This is because traditionally in SEM, we were always talking about the sigma matrix, right? The covariance. Historically, we haven't been talking about the means. We've only been talking about the variances. That's why by default, the intercepts are excluded. So if you look at the path diagram, by default, the triangles are excluded from SEM. And that's why Lavaan by default doesn't include the intercepts. So to replicate what we have in LM, we want to include 1. Okay, 1 meaning the mean, right? Now, this is optional too, okay? So just because I want to recreate the path diagram, that's why I said motive, the covariance of motive and motive, which is the variance of motive, right? What term is that? Well, that is this term here, phi, right? This is the variance of motive. Okay, so now we know that. What about the residual variance? Well, we don't specify that because it's unobserved, right? So let's see what it looks like in Lavaan output. So the key thing you want to know is that it converges, right? You want your solution to converge, okay? You want your solution to converge. So it says after 14 iteration, converge just means you found an optimal solution. The estimator is ML, okay? So that's the key thing too. I won't go over too much in detail, but just recall that linear regression uses something called least squares, okay? So ordinary least squares. It's not equal to ML, okay? That's the main difference between Lavaan and LM is that Lavaan uses maximum likelihood. This is important to note, the number of observations. Remember, we had 500. I'll talk about degrees of freedom, but basically, if you have a degree of freedom of 0, it means you have nothing else to play around with, and that's called a saturated model. Now, the other stuff isn't as important. We're going to go down. But this is basically the output that we match, right? This is exactly the same coefficient. We got 0.53 from LM. The intercept we got, right, the read. Now, this is new, okay? This is the intercept of motivation. We didn't actually get that from LM. Now, the key thing to note are these variances. This variance of motivation is phi 1, 1, right? Now, what is the difference you see in the syntax between motive and read? You notice this little circle here? That means it's a residual. Okay, so if it's a residual variance, it's called psi, right? Psi 1, 1. So just know, why is it a residual? Because it's being predicted by motivation, right? So it's what's left over. So just think of it as what's left over from the prediction of motivation. It's stuff that's not being predicted by motivation in the reading score. And that's a residual variance. You'll see residual variances with a star. I mean, not a star, a period. Okay, so you should be able to map every term here to this path diagram, except the mean of the motivation. Any questions about how to run a simple regression in Lavaan and what the difference is between Lavaan and LM?
I had a quick
Yeah.
question about when in Lavaan, because you kind of mentioned interactions.
Yes.
And my understanding is it's harder to look at interactions in Lavaan than it is in LM. Or is that not true?
Yeah, I think, because we were talking privately, interactions are not as straightforward in Lavaan, only because you have to break down what we call simple effects. We won't go over interactions today, but basically, if you have interactions, I recommend using a package called EM_means. And I have a seminar on interactions. If you search decomposing interactions in R in Google, you'll find it, okay? Decomposing interactions in R. I'm pretty sure some of you have seen that page. But basically, use the EM_mean function to deal with interactions. And I highly recommend starting with LM to deal with interactions rather than Lavaan. Okay, any other questions?
Yeah, sorry. So
yes.
I understand, I'm very familiar with LM, and I guess right in using Lavaan, we're specifying things further. It's not clicking in my mind right now, but what would be the difference in specifying and not specifying? I guess like specifying the variance, for instance, like what if we didn't do that, what would that do?
Yeah,
that's change.
That's a really good question. Yeah, totally. Yeah, I get it.
Same thing with the intercept as well. It's like, so it just means that it's not centered on anything, right? So that there's, I don't know what the interpretation might be. That might be for.
That's a great question, actually. I think in Lavaan, just because you don't model the intercept doesn't mean it's not estimating it. So it's not that you're forcing the intercept to be 0, but you could correct me on that. But the convenient thing is because we set it to 0 anyway, so it doesn't really matter. But let's say we don't put this one term here, and let's say you don't put the variance term here. Then what's excluded? Well, basically you won't get the intercepts at all. So this goes away. And then you won't get the variance of motivation. So that goes away. Okay. So basically you'll just have the regression path and then you'll just have the residual variance. And that's basically what you'll get. You can verify if that's correct, actually. That's a good exercise. But the reason why intercepts are not modeled is because in lavaan or SCM in general, we don't talk about the means as much. But that's a great question. And I recommend just trying it out and seeing because that's what I had to do too, is like what's included and what's excluded. Just try it out and see what you get. And actually, you'll note something else, which I really won't talk about in detail, but the number of free parameters here will change depending on what you put in. Okay, so that's something to know. I won't talk about it, but it's something to know. The only reason I added those optional terms was because I wanted to model this path diagram. Did that answer your question?
Yeah, but so what is the purpose of the variance term, I guess, or what does that provide to us, or what is the interpretation, I guess, in that, or I guess relative to what we're trying to do?
The variance of this one or the variance of this one?
Well, the phi 1, 1.
Phi. That is the variance of the exogenous variable. So let's see. I think I discussed it here. So you look at this. So you've done probably you've used the VAR function in R before, and that's literally just the sample variance, right? And if you look at the sample variance of motivation, it pretty much matches the variance that you get out of here, right? So think of it as kind of getting the sample variance, except you're putting it into this model, so there's some rounding kind of error issues. Does that make sense? So because it's exogenous, it's basically a sample variance. Now, if it's endogenous, it's not the sample variance anymore. So if you take the variance of y of the read variable, you're not going to get the same residual variance. It's only approximately the same if it's an exogenous variable. Did that answer your question?
Yes, thank you.
Okay, yeah, and honestly, you don't have to do these variances at all. It's just good to note because this is what a path diagram technically looks like for a linear regression. And so you may not have seen this path diagram before for linear regression, and that's why I wanted to model it explicitly. Any other questions? Okay, so we've done simple regression. Now let's move on to multiple regression. And I'll go over this quickly because I think you guys know what multiple regression is. But basically, instead of having one exogenous variable, we're going to have more than one. But how many endogenous variables do we have? We always have one. Okay, so when we're talking about multiple regression, we're not talking about multivariate regression, which is multiple outcomes. We have multiple predictors predicting the same outcome. So that's basically what you need to get clear is it's only one outcome and multiple predictors. And that's what we have here in this path diagram. We have two exogenous variables here predicting one endogenous variable. These are observed, right? Because they're square. So they're square variable, meaning they're observed. Now, I think what Ryan was asking, okay, we have the variance here, right? We have the variance of the exogenous variables, but note that we also have the covariance. That's probably something you haven't seen before in linear regression is it actually implicitly models the covariance between X1 and X2. This is, for example, like motivation and what's this? Parental psychology. Okay. That's probably not something you've seen before in linear regression output. But if you've heard of like collinearity, that's basically why, because you are actually relating the X1 and X2 variables. But it's not explicitly modeled. That's the thing. It makes you rethink what linear regression and multiple regression is. Now, these are the paths, right? In regression, these are like the beta 1 and the beta 2, right? We call it gamma here. I'll show you why later. Predicting only one outcome. There's only one outcome, so there's only one residual variance, right? Okay, so in terms of specifying in lavaan, it's so much simpler than what I'm saying. You literally just add a term there, okay? again, this covariance is optional. What covariance is this? This is phi, right? And 1, 2 means the first variable with the second one, right? So the first exogenous variable with the second. That's all that is. And what we get out of Lavon is basically an additional coefficient, right? So p-psych. So p-psych has a negative relationship with reading, remember? Parental psychology, negative parental psychology is negatively associated with reading. How many residual variances do we have? We have 1 residual variance. How many exogenous variances do we have? We have 2. Okay, because we have 2 exogenous variables. Let me see, any questions about that? Let me see if you get what I'm saying in simple regression. Let me launch a quick poll, if you don't mind. This is simple regression. So model 1A just means simple regression. So in model 1A or simple regression, there's 1 endogenous outcome and 1 exogenous predictor. In model 1A, Y1 means that I have 1 observation or student in my sample. This is kind of just making sure you understand what the notation means. And again, you don't have to respond, just kind of testing your understanding a little bit, but if you get it wrong, no worries, okay? That's totally fine, and just understand what you got wrong in terms of your concept. I feel like most of you are getting it right, so that's good. Okay, I'll close the poll in about 10 seconds. 5, 4, 3, 2, and 1. Okay, so yeah, in simple regression, there's only 1 endogenous outcome and 1 exogenous predictor. That's true. And then in simple regression, Y1 means that we have 1 variable, okay, not 1 endogenous variable, not 1 student, okay? So it's basically a variable that contains 500 students, but I didn't show that in the equation. So very good job on answering that. Thank you. Any questions on simple or multiple regression? I went over quickly there because I assume that you know those models. Okay, so this is where maybe it's a little bit newer. Maybe you guys have heard of this, but it's basically multivariate regression. I call these model 3. Multivariate regression models multiple outcomes, not necessarily multiple predictors. So this is the general multivariate linear model. So y is a function of alpha, the intercept, plus gamma, the regression coefficients, times the exogenous predictor, plus zeta, right? It's the same model what we've seen before, except now we have what we call matrix notation. So the bolded means I have a vector. A vector means something with more than 1 element, right? So for example, the vector here is y1, y2. What does that mean? That means I have 2 endogenous outcomes. Each of these is defined by an equation, okay? The equation is alpha plus gamma x plus zeta 1. Now, if you do some matrix multiplication, you'll see basically, you know, gamma 1, 1 and gamma 1, 2 means the 2 predictors of y1. And then gamma 2, 2 is the predictor of y2. If this doesn't make sense, I'm going to show you the path diagram. I like pictures, so I'm going to show you the path diagram. So notice what's the same and what's different. I like just comparing what's the same and what's different. Well, the same is, you know, this this, all these are the same, right? Anything in the X is the same, right? This is part of multiple regression. What's not the same? These, right? You have more than one outcome. So y1 is an endogenous variable and y2 is an endogenous variable. Here, y1 is read, let's say, and then y2 is math. I think x1 is parental psychology, and x2 is motivation. Okay, so you're saying that parental psychology and motivation simultaneously predict reading, but only motivation predicts math. That's your hypothesis that you're testing. Now, the important thing to know is this gamma, right? Remember the gamma. So the first index is telling you basically which variable, endogenous variable you're predicting. The second index is telling you which exogenous variable you're predicting. So you kind of have to read it backwards. So 1 here means y1. 1 here on the right means x1. Let's look at the other one. 1 here means y1. 2 here means x2. So the second predictor predicting the first outcome. And 2 just means the second predictor predicting the second outcome. Does that make sense? It might be a little technical, but this is basically how you read the regression coefficients. The additional thing you may not have seen before is this. So we've seen the residual variance. We have not seen the residual covariance. So by default, Lavaan will correlate the residual covariances, or will covary the residual variances, okay? That's just something to note in multivariate regression. And why do we care about that? Because basically then you interpret your regressions not as separate regressions, because if you didn't have this term here, you would basically be running 2 linear regressions. But the fact that you're saying, I want to correlate the residual variances, that means I assume that there's some covariance even after accounting for, motivation and with parental psychology. So there's things over and above motivation and parental psychology that account for the covariance of arithmetic and reading. Does that make sense? Over and above the effect of motivation and psychology, there's something else explaining the covariance of reading and of arithmetic. That's actually unique to the multivariate regression. Any questions about that?
Yes.
Yes.
So, hi. So basically, if you wanted to draw the intercepts for y1, y2,
yes,
you just put like a triangle to y1 and triangle to y2 separately?
Yeah, or you can just have the same triangle because they're just ones, right? Except this one's alpha 2 and this one's alpha 1.
Great, thank you.
Okay, yeah, great. Good question. Anyone else? This might be a new model for some of you, especially for me when I first saw it. So, but yeah, it's basically 2 regressions, but then you have a residual covariance. That's basically what you're doing, okay? All right, let's see if you have. Okay, let's see if you understand what I said there with this poll. And again, like, don't worry if you don't get everything correct. That's okay. Oh, let me see if I messed up on what I mean by model 2. Yeah, and don't worry if you get everything, because I probably even messed up on the model there on the second one. Yeah, okay. Try your best to answer number 2. I don't know. I don't know if I made sense in that one. Vector. Or just ignore model question 2. if it doesn't make sense. Okay, great. I'm going to close the poll in 5 seconds. 5, 4, 3, 2, and 1. Okay, so you guys are correct about gamma. That's perfect. Yeah, it's basically the first outcome predicted by the second exogenous variable, right? That's perfect. Ignore two. I think what I was trying to say was this current model, but in the multiple regression, the alpha is only alpha 1, right? But in multivariate regression, the alpha is actually alpha 1 and alpha 2. Okay, so you have 2 intercepts. And then finally, the dot arith is basically the variance of the residual, not of the variance of the variable itself. Okay, so I probably need to go over that a little bit more, but basically this is the output of Lavand, right, from the multivariate regression. So you'll notice, this is the gammas here. All right, this is the residual covariance, right? So that's that residual, that's the psi1, 2. The part that's probably here that you missed here was basically if you have a dot in front of it, these are the residual variances, not the variances of the actual variable. Okay, not the exogenous variable. So let me just briefly go back to the path diagram here. So when we're talking about the covariance of this is, let's say this is arithmetic and this is reading. It doesn't matter. I think I flipped the labels back and forth, but if the concept is this, if you have the covariance of arithmetic and reading, that is not the covariance of arithmetic and reading. These are not the same thing, right? Because the dot means that I have a residual term. And what is the actual thing I'm covarying is the circle, right? The latent variable here, which is the residual, the unobserved variable. Okay. Now, if I wanted to do arith or reading, these have to be exogenous, meaning I'm actually covarying the exogenous variables. Any questions about that? Okay. All right, so I think what I'm going to do is skip over some of this multivariate, because basically I'm showing you in the following things that multivariate regression is not necessarily the same as linear regression, simultaneous linear regression, because if you run 2 separate linear regressions, LM separately, like if you can try it yourself, if you run LM here and then you run LM here again, you won't get the same results as multivariate regression. You will, though, if you turn this covariance off, right? So if you say then it's completely determined by the reading and arithmetic are completely determined by parental psychology and motivation, then and you assume that there's no residual covariance, then this is a linear regression, running 2 separate linear regressions. But I'll let you kind of, if you have time to kind of go over that. Otherwise, that's my main kind of idea there. So this part is a little technical, so I won't go over it in detail. But the thing you have to keep in mind is the degree of freedom. That's important. So the degree of freedom, I'll just go over very briefly. Right here. So the degree of freedom determines whether you have a model that's saturated or not. Okay. So saturated, again, means it's like a linear regression where I estimate every parameter in the model. So if you go back to the linear regression, you'll see that there's no room left over, and you'll see in the output that the degree of freedom is 0. If you have a degree of freedom that's negative, less than 0, that's bad, okay? You don't want that. You'll probably never see that in Lavaan because it won't even estimate. So that's bad. Degree of freedom less than 0 is bad. Degree of freedom equals 0 is neither good or bad. It's just kind of, it's called just identified or saturated. This is like your linear regression. This is like your multiple regression. Okay. Now, let's look at the multivariate model we were looking at before. I'm just going to scroll up real quickly. But I'm going to look at that multivariate model. So look at this degree of freedom here. Okay, so it's positive, right? So it's not 0. And trust me on this, if you compare it to the linear regression, you'll see that the linear regression is 0, the degrees of freedom. So what is the benefit of having a degree of freedom that's positive? Well, if you have a degree of freedom that's positive, then it means you have extra things left over to play around with, right? You can add another regression path. You can add another covariance if you want. Okay, so that's the benefit of having more degrees of freedom. This is called an over-identified model. And an over-identified model is good because this is what you need to assess model fit, okay, which we'll talk about later. So just a quick poll there. And I think after this, it's a good time to take a quick break. So just if you don't mind answering 2 questions, and then we'll take a quick break. So over-identified models implies degrees of freedom is positive. And then linear regression and multiple regression models are saturated models. Should be pretty straightforward. All right, I think you guys get this one. So I'm going to close the poll in 5 seconds. 5, 4, 3, 2, and 1. So yeah, I think you guys get it. But basically, over-identified models are good, right? Because the degree of freedom is positive, you have more room to work with. Linear regressions have degree of freedom 0, and that makes them saturated. So good job. So what I'm going to do is take a 5-minute break. So if you can come back at 2:22, and we'll continue from there. So yeah. And then if you have any questions, you can ask during the break. Otherwise, I'm going to step out for like 2 minutes. Okay, I'll be back at 2:22.
Lynn, I am having one question related to covariance between X1 and X2.
Yes.
This covariance will be a kind of variance inflation factor or what?
Oh, yeah. You mean like collinearity?
Yeah.
Yeah, that's something to consider, but it's not something we regularly assess in SEM. It's definitely something you can assess in linear regression in general. The fact that we only have 2 predictors, though, I don't see it as a big problem. It's usually a problem when you have a lot of predictors.
Okay, we can ignore the collinearity between the exogenous variable in SEM.
Not ignore, but you know, just consider that it is accounted for by this covariance. Okay.
Okay.
And there is no variance inflation factor in SCM. So that's why I recommend just running it as an LM model and then doing the collinearity diagnostic there and then going back to SCM.
Okay. Okay. Thank you.
Yeah. So yeah, all the concepts in linear regression apply to SCM, right? So it doesn't mean just because you put in SCM, then it's no longer a linear regression and doesn't have collinearity. Okay, so those are all related to each other. Okay, so any questions before we start back up?
Could I ask a question?
Yeah.
Sorry if I missed this. But why is alpha always 1?
Oh, okay. So basically it's not 1, but it's just like it has a 1 in front of it because it's an intercept. Yeah, and then when you look at the syntax to Lavaan, you'll notice that we always add a 1 here, right? That's kind of like the alpha. Okay, so it doesn't mean that it's 1. It just means it's 1 times that. Okay, and honestly, we have 0 here. So it's not 1, but it's because the intercept itself is 0. So 1 times 0 is 0. Does that answer your question?
Right. So even if in the equation there's no term that 1 is being multiplied to, it means 1 times alpha?
Yeah. The 1 is like this 1 here. I didn't draw it, but it should be 1 times alpha. Yes, exactly. Because alpha is the path, right? So if you think about just 1 being the main thing, and then the regression path of that 1 is alpha. So it's like this. 1, right? That's the variable 1, and then the regression coefficient is alpha. This is alpha 2.
Okay, and the alpha would differ based on the data because it's the mean.
The alpha 2 will differ, yeah, for sure. Now the 1 is always 1.
Okay.
Yeah, the 1 is always going to be 1. If you talk about the intercept, it's always 1. Think of 1 as another variable, and that's why it's like a triangle. Okay,
thank you.
Mm-hmm. Any other questions? Great. Okay, I know this material is very dense, so like just bear with me, and I promise this is like more than you ever thought you would learn about SCM in an intro class. It's probably one of the more technical intro classes I've seen personally. Like I know I've attended some intro SCM classes that focus more on like the syntax and but for me, like I want you guys to understand kind of more under the hood rather than just like how to like run this in Lavaan. Because honestly, it's so easy to run this in Lavaan. Look at all we're doing. We're just saying like M4A, you know, this is read predicted by psych and motivation. That's it. That's all you have to do in Lavaan. So the syntax itself isn't hard. It's really understanding like what the syntax is. Okay, and that's really why I'm going over this. It's not worthless for me. So hopefully you find it helpful to go through all this kind of technical detail. And that's actually something we're experimenting. We usually don't go over such technical detail in AG seminars. So if you have feedback about that, let me know, okay? If you want more of this or just you don't really want the technical details, also let me know, okay? All right, so we've talked about linear and multiple regression. We've talked about multivariate regression. Now, you probably heard this model before. It's the path analysis model. When I was learning SEM, I kind of confused path analysis models with multivariate regression models. But really, it's just subtly different. There's something else different, and I'll tell you why. So again, we have the same model where we have a vector of endogenous variables, right? This is the intercept, like like someone was asking. And then these are the regression coefficients. And then this is the exogenous variables, right? What's the extra term we have here? We have this B term, okay, this B matrix. What is this B matrix? Well, you see it's being multiplied by an endogenous variable, Y. So you're thinking, how can an endogenous variable predict another one? Well, that's what path analysis allows you to do, is it allows you to predict an endogenous variable to another one. Not to itself, but to another one. So gamma is a relationship between exogenous to endogenous, okay? Beta is a relationship of endogenous to other endogenous variables. To read it, it's the same thing. So beta 2, 1 means I'm predicting the second outcome with the first. So Y2 on Y1, okay? It's the same reading as gamma. So you already know that. So you see in the path diagram, the only additional thing is that now Y1 predicts Y2 as well. So you can have a regression path of 2 endogenous variables. That's fine in path analysis. That's the main difference between path analysis and multivariate regression. Okay. And then this is just what it looks like in terms of matrix form. But basically, what are these? These are the diagonal paths. So basically, this is like beta 1, 1 and beta 2, 2. Can you actually have that? Well, beta 1, 1 means you're predicting Y1 to itself, which just doesn't make sense, okay? And then beta 2, 2 means you're predicting Y2 to itself, which doesn't make sense. So you typically see 0. I don't think you can even have non-zero entries here. And then is it symmetric? Meaning, is the lower and the upper the same? Well, is beta 1, 2 equal to beta 2, 1? And I say it's not, because beta 1, 2 means you're predicting Y2 to Y1, and beta 2, 1 means you're predicting Y1 to Y2. Okay, so they're not the same. That's why we have a 0 here. Okay, any questions about that? That may be a little technical. All right. And let me know if I'm doing too many polls, by the way. But I like polls because I like seeing kind of if you, oh, I don't have a path analysis. Okay, so no path analysis poll there. All right, so we're gonna skip that poll. Okay, so this is how you model path analysis in Lavaan, right? It's really easy. Okay, so what's the only term that we added? Well, reading here is a endogenous variable, observe, right? And reading here is now an exogenous variable because the right-hand side is exogenous, the left-hand side is endogenous, okay? That's all you have to do in the Lavaan is to treat it as if it was an independent variable. But you know that this is an endogenous variable predicting another one. And so basically you have this additional path here. So reading is positively associated with arithmetic. So 1 unit increase in reading results in a 0.573 increase in arithmetic. Okay. So in Lavaan, path analysis is not that bad. And that's why I confused path analysis with multivariate regression, because I didn't know the difference between an exogenous and an endogenous predictor. But that's basically the difference. Okay. Any questions about that? So that's path analysis. Not too bad, right?
Could you just
yeah.
Could you explain? It was really clear when you were explaining the path analysis with all the variables in it. Can you just articulate what the interpretation would be?
Yes, yes, that's a good question. Okay, so let me go back. I have some notes. So I'm going to go back to that. Yes. Hold on here. Okay. So let me, because even for me, sometimes I'm like, which variable am I looking at? Okay. So let's go back to the path diagram. Okay. So I am also looking at another screen of my Lavaan code. So I know what I'm talking about here, okay? So this is M4A in the Lavaan code. So reading and arithmetic are both outcomes, right? So let's make sure we get this right. Reading should be Y1, and that's a good exercise to map the variables to the Lavaan output. So that means arithmetic is Y2, right? How do I know that? Because I make reading a predictor, right? So this has to be Y1. Okay, well, let's see. Psych predicts only reading, right? Psych predicts only reading. So it must be this one. It's like a puzzle, right? You kind of have to figure out the puzzle pieces. So psych predicts only reading. But then motivation predicts both reading and arithmetic. So it must be this one. Did that make sense?
Yes.
Perfect. Okay, so now you know how to read all these terms in the Lavaan output. Okay, and the reason why I didn't put the actual things in there is because this is what you'll see in like textbooks, the Y1, Y2, rather than like the actual variables. So it's good to kind of be able to translate between the Lavaan and the path diagram. Okay, so good question there, because sometimes I forget what the variables are too.
Wait, I actually meant, sorry, I meant, could you go through the interpretation of
Oh, the interpretation, yes. Okay, so now that you know the path diagram, let's go over the interpretation. So the interpretation is basically the same as you would interpret a linear regression, okay? So for example, right here, for 1 unit increase in negative parental psychology, there is a 0.275 decrease in reading scores predicted on average. For 1 unit increase on motivation, there's a 0.461 increase in reading. So reading and motivation are positively associated. So now we have one outcome here, okay? Now for the second outcome, then motivation is positively associated with arithmetic and reading is positively associated with arithmetic, okay? The intercepts are basically 0 because we found that to be true in our data as well. And then now these are the residual variances of reading and arithmetic. What are these? So these are basically what's left over, right? So in terms of arithmetic, then it's what's left over. Let's go to reading first. In terms of reading, the residual variance is what's left over after accounting for parental psychology and motivation. So what's the variance that I can't explain with parental psychology and motivation on reading scores? There's probably other factors that contribute to their reading score, right? Maybe it's basically their emotional stability. Okay, that might be another reason. So if they're more stable, they're more focused in class, and their reading scores go up. So we haven't accounted for that, and that is basically why we have a residual variance. Now for the arithmetic, we have the effect of reading and motivation. Okay, so basically this is the residual variance accounting for reading and motivation. Okay, so it's what reading and motivation haven't accounted for, and what's left over. So maybe motivation and reading are not enough to predict arithmetic. Maybe it's negative parental psychology, which we didn't account for. Maybe a parent yelling at their kid is going to make them decrease their math score. So we haven't accounted for that there, and that's why we have the residual variance. Did that answer your question?
Yes, thank you.
Perfect. Okay, good. Any other questions? Yeah, and so basically what I'm saying is that, you can interpret the coefficient as if you were interpreting a linear regression. And that's basically what it is a set of linear regressions. Okay, this might be new to you if you haven't heard of SEM models. This is called the modification index. Okay, so model 4A is basically the path analysis, right? And then also model 3A and D are the multivariate regressions. You notice what's in common between them is that they have a degree of freedom greater than 0, right? That's positive. And what does that mean? That means we have leftover room to work with, right? These are over-identified models, as you guys kind of answered already. And that means we can add more terms, right? Why do we need to add more terms? Because sometimes you have a model that's not a good fit. Okay, and we'll talk about model fit. But basically, if you don't have a good fitting model, you want to try to improve your model fit. And what a modification index does is it basically does a lot of like 1 degree of freedom tests, meaning I'm going to add 1 parameter at a time. Okay, so if you use this mod indices function in Lavaan, you'll see it. But basically, what this is saying is this is a 1 degree of freedom test. This is a all of these are 1 degree of freedom tests, meaning if I added this into my model, I would decrease my degree of freedom by 1. So if I had 1 degree of freedom before, it would be 0. Okay. What does this mean then? It means I'm going to add motivation on the left-hand side, and the operator is the prediction of arithmetic on the right-hand side. That means arithmetic is the exogenous variable, and motivation is the endogenous variable. The tilde means it's a structural regression, but arithmetic and motivation are observed, right? So these are observed variables. So basically adding another regression where motivation is the outcome. Now look at the modification index. It's 68. That's really big. Okay, really big. So let's go back to the path analysis and look at that. So I'm going back to the output. Look at the chi-squared, okay? So I haven't really gone over this, but this is under the model test user model. This test statistic is supposed to be chi-square distributed, okay? So when I talk about a 1 degree of freedom test, I'm basically saying I'm going to subtract 1 degree of freedom and I'm going to add a parameter. Because when you add a parameter, you decrease the degree of freedom. But that modification index was 68 points, right? Meaning I'm going to drop my chi-square by 68 points. And that leads to a negative chi-square, which doesn't exist, okay? So basically what I'm saying here is that modification indices don't always make sense. And it really, you need to consider your theory to drive kind of why you're putting in this extra term. Well, this doesn't make sense to me, but maybe this one makes sense. So arithmetic, and because I have arithmetic as an outcome, and I just want to add parental psychology as an exogenous predictor. And look at the MI, 4.8. If you recall, the test user test statistic is 4.87, right? So basically, it drops it down exactly how I expect, which is 4.8. And that becomes a saturated model. So MI is that chi-square difference. And then EPC is the expected parameter change. That's how much I expect the parameter to change. So for a 1 unit increase in PSpsych, I expect a 0.068 increase in arithmetic by adding that, okay? These you don't have to consider because these are just standardized versions of EPC. One is by the latent variable, one is by all of the variables, one excludes the X variables. You don't really have to know that. Are there any questions about the modification index here? In terms of like what it's saying in the output? Okay, so basically, like I said, not all modification indices make sense. This one didn't make sense to me. And these don't really make sense to me because I'm not improving anything by doing that. So these are 0, meaning I'm going to change my chi-square at all by adding this. So why is it there? Okay, so you have to decide what terms to add in. The modification index isn't telling you exactly what to do. That's the other thing too, is you want to make sure that you're not like over using the modification index, okay? I think I have that somewhere, but basically this is a caveat, okay? Just because the modification index tells you, I have it down here. Just because the modification index tells you that you should add this parameter doesn't mean you can just add whatever parameters you want. What I see a lot is people, they add all these like residual covariances like these, and they add tons of those, right? That does improve your model fit, but doesn't mean anything, right? Have you hypothesized that covariance in your previous model? I mean, in your hypothesis. If not, then why are you adding it in? Okay, you have to have a solid reason. The thing is, if you add more things in, the probability of finding a false positive increases, right? It's called type 1 error. So it's like, even though I'm gonna fish, like, and I catch a lot of fish, it's because I threw my line like 1,000,000 times, right? It doesn't mean there's a lot of fish. It just means I sampled too many times. Okay, so you overcompensate it, and that's actually not good. So Andy, I think 2 weeks ago gave a seminar on the consequences of type 1 error and for overemphasizing like the p-value, which we'll talk about, and that's something to keep in mind when doing modification indices as well. You don't want to overuse it and abuse it. Okay. Any questions about that? So yeah, if you have time, just try running it with that extra term there. So what I did here was I added that p-psych term, the parental psychology term in arithmetic, and then I saw like the change in the chi-square. But basically, you'll see that the degree of freedom is now 0, right? It is exactly what we expected. And then the EPC, do you see the EPC term here? It's right here, 0.068. That's approximately what we got before, okay? The reason it's approximate is because it estimates all those things simultaneously. So it's not exactly going to be right. Okay, so here's something for you to think about is why if we do the modification index in our saturated model, why is this empty? Okay, so that's something you can think about. Any questions about modification indices? No? Okay. Okay, so we talked about like altering our model, right? So this is basically where model fit comes in, model fit statistics, right? So you can change your parameters, the number of parameters you have using modification indices, but model fit statistics tells you if your current model is good or not. So remember our discussion about sigma and sigma theta, right? So sigma and sigma theta are basically the model. The sigma is the population covariance matrix, and then sigma theta is the model implied model covariance, right? Obviously, we want our model to reproduce our population. That's why that's the null hypothesis. And the alternative is saying then the model does not reproduce our covariance, okay? Now we talked about sample covariance. In the population, we have sigma and sigma theta, but in the sample, we have S, right? And then we have something called sigma theta hat. What does that mean? That means the model, the estimated model covariance, and S is the estimated population covariance. So like I say here, S minus sigma is a proxy of the model, the fit of the model, not sigma theta minus sigma. Why is that? Because if I solve for this equation, I get sigma theta minus sigma equals 0. That's always going to be 0, right? So there's no point in assessing the fit of that because it's always going to be 0. It's when you have an estimate. This S is not always going to be the same as sigma. This sigma theta is not going to, hat is not going to be the same as sigma theta. This term is called the residual covariance. Okay, so the residual covariance is not necessarily 0, but the closer you are to 0, the better the fit of your model, the more evidence you have that your model is well fitting. Any questions about that before I jump to the poll? Let's see. Oh, I guess I don't have that. No, I don't have that. Okay, I don't have that. Okay, so, but I do have the modification index poll. So I want you to kind of take that one. So each modification index has one parameter at a time. And then 2 fully saturated models must have exactly the same estimated parameters. Oh, that's good. You guys are getting it. Okay, I'm going to close the full poll in about 10 seconds. Don't worry if you don't have time to answer it. 5, 4, 3, 2, and 1. I think you guys get it. That's really good. Okay, modification index has 1 parameter at a time, definitely. So it's a 1 degree of freedom test. 2 fully saturated models must have exactly the same. That's not true because you can have a saturated model that has like different parameters, right? So remember we saw this modification index here where we had like all these things here that are the same, right? But these are different parameters, right? Okay, so you guys get modification index. All right, so let's go back to model fit. But I didn't do this on the poll, but I'm gonna answer myself. Okay, so the residual, true or false, the residual covariance matrix is defined as sigma minus sigma theta. And that is false, right? Because the residual covariance is always, of this is always 0. I mean, of this difference is always 0, right? If you take the difference. It's not the population, it's the sample. That's what you have to keep in mind there. Okay. Now, this is where the Lavaan part comes in. Okay, so we fit the path analysis model, right? And then we got that it was over-identified. Now, how do we get the model fit? You just add an extra like specification here called fit.measures equals true in the summary, and then you'll get it. Okay, this is not output by default in Lavaan. This is something you have to kind of request because there's honestly too much output already. So remember we had 1 degree of freedom left in our path analysis there. We had 500 observations. Okay, so the main thing you want to look at though is all these things that go under here. So this is new, the CFI. This is new, the TLI. We won't talk about these. And then this is new, the RMSEA. Now, if you've seen the CFA seminar, this is familiar to you, but we're going to talk about what that is. The other things you may not have heard of is this baseline model test, and we'll go over that a little bit too. But that's the additional output you get from Lavaan that needs kind of some understanding in order to interpret it, okay? So when we get this from Lavaan, we're going to get the model chi-squared, which is the user test model, model test user model. The CFI is called the confirmatory factor index, which ranges between 0 and 1. So the closer you're to 1, the better the fit. TLI is called Tucker-Lewis index. It's also between 0 and 1. And also closer to 1 is better. But 0.9, it has lower threshold for a good fit. And then the root mean square error of approximation. So you want this to be less than 0.05. I only report these because this is the most commonly reported fit indices. Now, there's other things like the standardized root mean residual you can also report, but that should be, you know, around 0.06-ish. But yeah, they're all kind of supposed to tell you the same thing if you do have a good fitting model. But I'm going to explain why we need these fit indices over the model chi-square, because that's basically what SEM started with, was that model chi-square. And yeah, there's a little bit of matrix notation, but it's not going to be that heavy. Basically, I'm going to explain that this is basically the model chi-squared fit statistic, okay? So when we talk about SEM, we have something called a fit statistic. A fit statistic is basically how well does the model fit. And remember these terms here, right? The S and the sigma theta, right? Remember, this is like the residual. Just think of it like it's a measure of how close to 0 this residual is. Okay, it's not exactly it, but you have these terms there, the same terms. The model implied estimated covariance matrix and the sample covariance. You want these to be close, right? So do you want these to be, this difference to be big or small? Do you want this to be big or small? Well, because you want the residual to be small, you want this to be small, okay? Okay, so what Joris-Cog proved in 1976 was that if you multiply the sample size by this fit statistic, this is distributed chi-squared. Okay, this is chi-squared. And that's why we always talk about chi-squared. And if you've seen chi-squared, it kind of looks like this, like a skew normal-ish. Okay, so that's why we talk about a chi-square. The larger the chi-square, the larger the difference the larger the difference between the sample and the sample implied covariance matrix and the sample observed covariance matrix. So that's bad, right? Okay, so it's kind of an opposite thing. We want our chi-squared to be small. Okay, so if you reject the null hypothesis, that's actually bad. Okay, so it's kind of like a counterintuitive rejection hypothesis. If you've done like chi-squared goodness of fit, you want that chi-squared to be, big, but then in this case, you want this chi-squared to be small. That's the difference of this and other models that you've heard of. Now, the reason why we don't use chi-squared is because chi-squared is sensitive to large sample sizes. So chi-squared is very sensitive when you have large sample sizes, meaning the chi-squared will be easily rejected. Okay. So basically, the recommendation from Klein is that you have a sample size of 20 to 1. Okay, so you have 10 parameters, then you're estimating about 200. So you want more than that, but you don't want it to be too big, otherwise you'll reject the chi-squared. Okay. Now, this is why we developed what we call approximate fit indices, because researchers in the past have realized like, oh, I'm getting rejection of a chi-squared every single time. So what should I do? Well, that doesn't necessarily mean your model is bad. It just means it failed the hypothesis test. Okay, it's not a give or take, right? It's not just yes or no. That's why we've developed approximate fit indices. So to understand that, let's just go over real quickly what a baseline model is, because that's important to understanding what an approximate fit index is. So a baseline model is basically, you can think of it as the worst fitting model. Okay, why is it called the worst fitting model? Because it assumes that there are no covariances between variables. So if we have, motivation and psychology, right? We basically assume that there is something here, but nothing in the off diagonals. Well, if that's true, then basically every variable is independent of every other variable. That's a bad model, right? Because unless that's actually true, that's a bad model. But the reason why we need the baseline model is because we want to compare our model to the baseline model. So you notice that these are now phi's, because these are now exogenous, right? We want to compare everything to this now, treating everything as an exogenous variable. And so I basically get only the variances in Lavaan, and then I assess the model fit and then see what I get. Look at this. So the model test is the same as the baseline. This is an artificial example where I made these the same, right? So that's how I showed you that this is the baseline model. Remember, this is the model where you don't assume any covariances between your variables. So there's no relationship between motivation and parental psychology at all, or reading and parental psychology. You're assuming that for your baseline model. Okay, any questions about baseline model? So again, think of baseline model as the worst model, okay? So the worst model, these are the worst models. Think of saturated models as the best models, right? So degree of freedom 0 means saturated, which is the best model. Your model falls somewhere in between. Your model falls somewhere in between, right? I mean, unless you have a saturated model, your model is probably in between the baseline model and the saturated model. So what an incremental fit index is basically assessing the difference between your model to the baseline model and the ratio of that to the saturated models of the baseline model. So if you look at this figure, I like looking at this figure because it kind of shows you. So if you had perfect fit, then that means you have the saturated model, right? So your blue bar would extend to here, right? So that would be perfect fit. Now, if you have bad fit, you're going to be close to the baseline model. So that denominator is, that numerator is going to be really small. So remember, a CFI close to 1 means good. A CFI close to 0 is bad, right? Does that make sense what this model is saying, an incremental fit index? I think this diagram makes it clear what that is. But if you have questions generally about the concept, let me know. Okay. So we talked about model chi-square. We talked about these incremental fit indices. Now, RMSEA is not considered an incremental fit index. It's considered an absolute one because it does not compare against the baseline model. Okay, so that's the only difference between incremental and absolute, is that they're both approximate fit indices, but absolute does not compare to the baseline model. So I won't go over too technical, but basically the CFI is basically comparing the baseline to the user and then the baseline to the saturated, right? But why is this 0? Well, okay, what is delta? Delta is basically the chi-squared minus the degree of freedom, right? So if your chi-squared equals your degree of freedom in the saturated model, which is 0, then that means you have a saturated model, and that's why it's 0 here, okay? So that's why there's no saturated model in this. But you see it's kind of like the same concept, baseline minus user over baseline minus saturated. Okay, so that's the general concept of CFI. And then you can check if you just run the calculations if you get the 0.994. That's pretty good. And then for the TLI, we kind of get the same thing, right? It's the baseline minus the user over baseline minus the saturated. Now, in this case, the saturated is 1. I won't go over the details, but basically, it's a ratio now. Okay. And what you need to understand there is these are basically incremental fit indices because they kind of test the fit in the same way. That's why CFI and TLI are usually presented together. Now, RMSEA is kind of the different one because it's not an incremental fit index, it's an absolute one. And basically, it does not compare to the baseline model, okay? It just has this term here, which is kind of like the numerator of the CFI, but the denominator is not a function of the baseline model. You see that? It's just the degree of freedom times n minus 1. The important thing to know about RMSEA is that you want RMSEA values less than 0.05, less than or equal to 0.05. That's close fit. And then between 0.05 and 0.08 is reasonable, but fails close fit. And then greater than 0.10 is bad. Okay, so in our case, we have 0.088. That's reasonable approximate fit. Any questions about, I know I went over this kind of quickly, but I did cover this in the CFA. That's why I kind of wanted to like speed up this one. Basically, you want to just compare your CFI TLIs to be greater than 0.9 or 0.95. And then you want your RMSEA to be less than 0.05-ish. And in this case, we're close, okay? But just note that also we rejected our chi-square, right? So that's why we have these incremental or approximate fit indices, because usually you reject your chi-square, and then you can show using these approximate ones that actually it is not bad because it's a continuum. Okay, any other questions before we take our final break? I know it's a lot of material, and then we just have 2 more models to cover and we're done. Okay, so let's take a 5-minute break and we'll come back at 3:06. Yeah, so we are going to post the recordings, but it's going to take a couple weeks because we have to do the closed captioning and it takes a long time to do that. So bear with us and then we'll try to get that out in like a month or two, okay? Yes, and that's our YouTube channel. By the way, thanks, Andy, for answering all these questions. I can't really see the chat while I'm talking, so that's really helpful.
You're welcome, of course.
Yeah. But it looks like you guys are thinking a lot about SEM, so that's good.
We actually came up with how to diagram the.
I saw that, yeah.
Yeah, while you were talking, yeah.
Nice.
So
does it look like mine?
They're more primitive looking,
okay.
but yeah, they actually look okay. Yeah,
okay.
It's about the quality, almost quality of M+.
Nice. Yeah, now you know how to read a path diagram, so it's perfect. Lavaan is definitely not the best package in general because
R, it might be, though.
huh?
For R, maybe?
In R, it is not the best, but it's the easiest one to use. I would.
What do you think the best in R?
You know, there's very like technical programs called like OpenMX, and that you can pretty much like program your own SEM. That's like if you really want to go like technical. But I would say, and then there's also the SEM package in R. But honestly, I feel like Lavaan is the easiest to use. The reason I say it's not the best is because I don't think it does categorical indicators very well. So like logistic regression or things like that.
Francisco, we're not so well versed in Python, so I can't answer that for you. Sorry.
Yeah, I don't know if there's one in Python actually. But M+ is the best program for SEM in general, if you're curious. Okay. Any questions before we go back? Thanks for staying, by the way. I know it's a lot of material, like dense material. So if your brain hasn't been fried yet, just thank you, and hopefully we'll get through this. I know it's a lot. Okay. All right. So we're just going to talk about 2 more models and we're done. And then you'll kind of at least know how to identify the major types of SEM models. Okay, so basically, we have now the measurement model. We talked previously about structural paths between observed and observed variables, right? So we got about linear regression, multiple regression, and then we talked about path analysis, multivariate regression. Those are all observed to observed. Now, like I said before, measurement models are basically observed to latent, right? So you have a circle predicting a square. And this is in a measurement model. Okay, this only exists in the context of the measurement model. So what is the equation of that? So basically it is your X now as your endogenous variable. So usually we have Y, right? But why do I put X here? Because this is technically an exogenous variable, like I said before. But it is being predicted by something that's not observed, which is the latent variable. So this is now, instead of alpha, we call it tau. Okay, so this is called tau for t, intercept, I guess. And then lambda now is kind of like our gamma, right? Our gamma was our regression coefficient. Now we have lambda, which are the regression coefficients of our latent variable c on our outcome x. So these are called the loadings. This is called the factor. This is called, I guess you could call it disturbance, or it's also like a residual, but that's delta. So if that's not clear, we're going to go over the path diagram. This is a 3-indicator model. Okay. This is a 3-indicator model where we have 3 X's. Okay. And this could be, you know, like motivation, stability, harmony. And then this could be adjustment, right? Kind of what we went over before. Okay. Well, then this looks like a regression, doesn't it? Well, what's the regression? What's the outcome? The outcome is the indicators, the X1, X2, X3, motivation, stability, and harmony. What is the predictor? The predictor is the C, the adjustment variable. And then these are the loading, the regression paths, right? Because these are technically outcomes, they have a residual, each of them. And because they're unobserved, they have, and they're latent, they also have a variance, right? So these are basically the residual variances or disturbances, you can call them, of your indicators. Because this is an exogenous variable here, this has an exogenous variance. Okay, so these are the loadings, these are the residual variances, and the exogenous variance. Any questions about that? Let me see if you can answer all of these. Okay, no. Okay, let's go move on. So this is important only because we're talking about a latent variable, right? Because we don't observe C, which is adjustment in our case, right? We don't observe that. So because we don't observe that, we have to make some constraints, okay? So this is called identification in factor analysis. So there's 2 ways to identify a factor. There's one called the marker method, and then there's one second called the variance standardization method. The marker method fixes the first loading of each factor to 1. The variance standardization method fixes the variance of the factor to 1, but freely estimates all the loadings. So let's go back to the path diagram. The marker method says, I want this loading to be 1. And I want to free these. So that's marker method. Okay, does that make sense? So when you do marker method, it means you're fixing the scale at, let's say this is motivation, then you're fixing the scale at motivation. So whatever the scale of motivation is you're going to fix it, the latent variable too. Now, what's the variance standardization method? Variance standardization method means I want to constrain the variance to 1. Now all these are free. Now you can think of this as basically, you know, like a standardized variable where the variance is 1. Remember in like normal variables, if you have a standardized z-score, then what's the mean? The mean is 0 and the variance is 1, right? So it's kind of like that. So in a sense, variance standardization is more standardized. So when you look at the output, you'll see like LV, that means latent variable, that means variance standardization. But the default is marker method. So just note that, okay? The default is marker method, but you really want more like standardized variables. Okay, so this is how you do it in M+. I mean, not M+, Lavaan. Oh, here we want the indicators to be verbal, IQ, SES, and parental psychology. Okay, so it's like this, right? We know this. This is verbal, SES, parental psychology, and this is risk. Okay. Now remember the equal tilde means that we are specifying a relationship between a latent variable and its indicators on the right. Okay, so even though the arrows are pointing the other way, you want to do it the right-hand side for the indicators. Now, what is this? This is just saying I want the intercepts of the indicators. And then we don't have to specify anything else because it's all given to us. Okay, so you want to put this model into SEM. And then you can also use CFA, but it's just a wrapper for the Lavaan. And then you summarize the output. Now, the key thing here is you want standardized equals true, and then we'll see what that does. So any questions about the syntax of R or Lavaan for factor models? Syntax is pretty straightforward, right? Now you notice the degree of freedom is 0. This means we have a saturated model, right? So that's actually okay, right? Because three indicators is just enough. It's just identified. If you have 2 indicators, it's not identified. So look at the estimate here for verbal. This is basically saying we want to fix this at 1. How do we know that it's fixed? Because there's no standard error, there's no z-value, there's no p-value. So what method is this? This is the marker method, right? This is the marker method. Now, looking at this column, this is the variance standardization method. How do we know that? Because risk has a variance of 1, and it's not a dot, so it's an exogenous variance. Okay, so this is marker method. If you read down the column here, this is marker method. If you read down the column here, this is variance standardization method. Now, what's this? This is kind of different. This is standardizing by both y and x, and in n plus notation, or you can say kind of like endogenous and exogenous. So if we standardize basically by the indicators and the latent variable, this is what we get. Right here, standardize all. This is actually more helpful in terms of interpreting loadings, because then you can say -1 is the minimum and 1 is the maximum and 0 is nothing. Okay, so kind of like a correlation. Then a loading of around 0.8 is considered good. A loading of around 0.4 is considered bad. But then basically anything in between is like, eh. So here we have 0.4, between 0.4 and 0.8, right? So that's okay. How about this one? This one we have negative. Remember, parental psychology is negative related. So is that good or bad? Well, it just means it's the same magnitude, but it has a negative relationship. So it's actually kind of good, okay? So what's bad is like if you have 0.01, that's bad. So you want a loading close to 0.8 in terms of its magnitude or the absolute value. And then you see here, the variance is still 1 for risk, but then it's now standardized between 0 and 1 for the indicators as well, the residual variances. How do I know these are residual variances? Because of the period. Any questions about interpreting the columns of the output? Okay. Then in terms of endogenous variable or exogenous indicators, you can also have endogenous indicators. So remember the X side and the Y side? These are now Y side. How do I know this is Y side? Because it's pointing to the right. So if you remember that orange diagram, I showed you the path diagram at the top. This is pointing to the right, it's the Y side. This was pointing to the left, so this is X side. Remember that? Now, the only difference is that the indicators here in X side are called X's, and the indicators down below are called the Y's. Okay, so that's the main difference. Now, how do I define the endogeneity of an indicator? It's defined by the latent variable. So the latent variable is now called eta, okay, and it has a residual variance here. Now I didn't draw something important, right? And what didn't I draw? I didn't draw here a relationship between an exogenous latent variable and its endogenous latent variable. So technically you need to have this to have an endogenous variable, and that's why I didn't model it here. But in terms of every other term, you can interpret it the same way. These are still the loadings, except now it has a y for y side loadings. And these are still the kind of residuals, right? Except you have epsilon instead of delta. So you interpret it the same way, except now you have a residual variance. That's the main difference. That's how you know this is an endogenous latent variable. Any questions about endogenous or exogenous latent variables?
Excuse me, I have a question regarding the meaning of the endogenous and exogenous measurement models. So for the exogenous models, you use the exogenous latent variable. I'm sorry, use the exogenous variable to predict the latent exogenous variable.
Yes, yes.
So basically, it's I want to know the meaning of it. It's like a summarization of the observed variable or extraction of.
Yeah, that's a good question. Yeah, it's an abstraction. So I think I keep forgetting which variable. I think we used risk, right?
Yes, risk.
Okay, so basically, once you have the measurement model, you don't have to think about the indicators anymore. You just think about it as a construct, an abstraction like risk. And then once you have the indicators here, which this is going to be like spelling and math and reading, you don't have to think about that anymore. You just call it achievement. Okay, so then once you have the latent variables, all you have to say is risk positively predicts or negatively predicts achievement, let's say. And that's all you have to say because you already assume that the measurement model holds, which means then you don't have to consider the indicators. Does it make sense?
So the exogenous model was a step for the further models.
The measurement model, yeah, the measurement model.
Yes. Yes. So this is the measurement model is like a step for a model. So this is not the final one. So this is like a preparation.
Yes, well, some people just stop at the measurement model because they just want to see, you know, if this scale is a good measure. So some people just stop there and then they don't move on to the structural model. Now, other people who hypothesize, okay, I want to see the relationship of latent variables, that's when they move to the structural model.
Okay, I see. Thank you.
Yeah, good question. Any other question? Okay, so I have a poll finally, if you don't mind. So number one is C, latent exogenous variables do not have residual covariances. Number two, X variables, exogenous indicators do not have residual covariances. And then number three, in a list row path diagram, endogenous latent variables have right pointing arrows to the indicators. And then in list row, because all indicators are being predicted by latent variable, all indicators are classified as endogenous. This might be kind of tricky, so take your time a little bit on this one. I'll give you guys maybe 10 more seconds. Five, four, don't worry if you don't have the answer. 3, 2, and 1. These are really tricky, sorry. Oops. Okay, so actually, you got the first one. So latent exogenous variables do not have residual covariance, right? Because basically, no exogenous latent variables never have covariances. So let's look at the, I don't know if you can see this, but it's blocking this. Okay. Yeah, so I don't know if you see the webpage, but this is 511, right? So there's no residual covariance there. Okay, X variables do not have residual covariances. That's false because, just because these are called exogenous indicators doesn't mean they're not being predicted by, something, right? And in this case, they do have exogenous, they do have residual covariance or variances. And those are called theta deltas. I didn't really go over that too deeply, so don't worry if you didn't get that. Okay, in a literal path diagram, endogenous latent variables both have right pointing arrows, and that's correct because they're y-side measurement models. All right, so these are right pointing arrows. Right pointing arrows. Now, if it's left pointing arrow, it's a x-side measurement model. And then finally, because all indicators are being predicted by latent variable, all indicators are endogenous. That's false. You guys got it. That's false because we have an exogenous indicator in the model 5a, but it's still has it's still called exogenous. Okay, so you guys actually, I feel like you guys get it. That's great. Okay, thank you for answering that poll. Okay, so like the person said before, this is kind of like build up for the final model that we're looking at is the structural model. And the structural model, remember, is the defining relationships between latent to latent. So the structural regression model is between latent and latent variables. So we've seen 2 of these models before, and we know basically the last one. So we've seen these 2 models before. These are the x-side variable, the measurement model, and this is the y-side measurement model. We know what these are. Now, does this look familiar to you? Well, maybe. If you just replace the eta, remember eta is an endogenous variable. So let's just replace eta with y. Then y equals alpha plus gamma. Let's replace c with x and by plus zeta. Doesn't that look like a model that we've seen before? And if you know what that model is, feel free to put it into the chat. I'm just curious if you know. But yeah, it is a model that you've seen before. It's one of those models we did before with the observed variables. So the model I'm talking about is the path analysis model. Let's see, is there any different? No, okay. So yeah, the model I'm talking about is the path analysis model. Okay, doesn't that look familiar to you, the path analysis model? Remember we have the regression coefficients here, and then we had the other set of regression coefficients between endogenous variables. Okay, so you've seen all these kind of variations of these models before then. Okay, so this is just the matrix notation for it, but just know that these are multivariate models, right? So this is the x-side model, and this is the y-side model. So here we have 2 latent variables, okay? 2 latent variables, exogenous variables, being indicated by 3 indicators each, okay? And then these are the loadings. Now the loadings, you usually don't estimate every single one of them, right? So this is the unconstrained model. So you want to set some to be 0, right? Because you don't assume that every relationship here exists. The bottom one is called the y-side model, and that only has 1 latent endogenous variable. And these are the observed endogenous indicators. I like seeing pictures, so this is basically what it looks like. So these are the 3 exogenous indicators for C1. These are the 3 exogenous indicators for C2. These are the 3 exogenous or endogenous indicators of eta 1. So to make it clear, let's see if we can put in kind of the variables we looked at before. Okay, so let's look at this. So this is, for example, motivation. This is harmony. This is stability. Okay, so that is adjustment, right? What's the next one? These are exogenous. We also think risk predicts something, right? So risk is measured by verbal, parental psychology, and SES. What's the last thing? Achievement. We think adjustment and risk predict achievement. So then we have reading, arithmetic, and spelling. Okay, do all of these kind of make sense? And remember, gamma 11 means the first, and the only outcome predicted by the first and exogenous latent variable. And gamma 12 is the first and only outcome predicted by the second latent exogenous variable. Any questions about this model? Now, in every lambda, though, you want to identify it. Every factor needs to be identified. So if we just set Lavaan to the default, we're going to set these to be marker method, right? These are all marker methods. So we're going to set the loadings to 1. That's by default in Lavaan. Any questions on this before we move on to the syntax? Okay, I'm going to clear that. So, and this is exactly what I drew, okay? These are the 3 factors indicated by the corresponding indicators. And then this is the structural regression. Okay. The main thing you want to really interpret is the structural regression, right? The second thing you want to make sure is that the measurement model is well identified. Okay, so let's look at the output. So what method am I using here? Marker method. What method am I using here? Well, this is variance standardization method, but I want this to interpret the loadings. So this is standardization by Y and X. I don't mean Y and X in terms of the exogenous indicators. What I mean is endogenous and exogenous, okay? So that's just because Lavaan doesn't use literal notation. Okay, so look at the measurement model. So are these, first of all, is this identified? Yes, because we use the marker method. These are all identified. So every factor is identified. Now look at the loadings, the lambdas. So are the lambdas good? Yeah, I mean, this one's pretty good. This one's pretty good. This one. So all of them are between 0.4 and 0.8, right? So that's good. This one's even 0.9. That's actually really good. So what we've said here is that these are good indicators of each of our latent variables or factors. So that's good. Now that we've established the measurement model here, so these are all measurement models, right? Then this is the structural regression. And structural regression, now that you establish the indicator models that like someone said before, then you kind of just treat these as abstract concepts, adjustment, risk, and achievement, and then just kind of treat them as variables. So for a 1 unit increase in adjustment, I have a 0.375 increase in achievement. This is saying for a positive increase in risk, I have positive associated with achievement. We'll have to look at this one because this one is something that is counterintuitive, okay? So it's not necessarily true that you'll confirm your hypothesis. All right, so you can interpret this as basically like a regression now. Now the scale is kind of arbitrary, right? It's kind of standardized. But in terms of this is standardized by each of the indicators, right? And then this is standardized by both the endogenous and exogenous. So you have to be careful about which one you use because you get different output from this, okay? It depends on how you standardize it. Any questions about the interpretation of the coefficients here? Okay, I know, we're almost done. This is a lot of information I'm throwing at you and we're almost done. This technically could be like a whole course if you wanted it. Okay. The final model that I'm going to talk about today really is when you have two endogenous variables, okay? So think about the relationship of multivariate regression to path analysis, right? What was the only difference? Well, the only difference was that B, right? So B means I am allowing endogenous variables to predict each other. So here we have two endogenous variables. And now we have a beta, right, for the B, right? And what does beta 2, 1 mean? I'm predicting the second endogenous variable by the first endogenous variable. It's basically like the path analysis we did before, except now we have latent variables. And this is the model here. Okay. So again, the same concepts apply. We need to establish the measurement models first. And then we establish the structural regressions. Okay, but nothing else really changes. The only change is that we now have a beta term here. Okay, so beta meaning I'm allowing endogenous variables to predict each other. So then in terms of the output or the syntax, we still have our measurement models here, right? Now, which ones are Y side and which one are X side? Let's take a look. So adjustment, right? How do we know which one's Y side or X side latent variables? Well, we know that adjustment is on the left-hand side and achievement is on the left-hand side. So these must be Y side. Okay, these are Y side endogenous variables. And then these are the X. Well, that's not necessarily true, right? Because in terms of adjust, this is an endogenous variable. So the only X side is risk, okay? All right. Any questions about that? So once you understand that, then basically all you need to do is look at the output. The same concepts apply. We just have an additional endogenous predictor. And which one? See if you can spot the endogenous predictor. Well, the endogenous predictor must somehow lie in this, right? Because this is the structural regression. The things above here are the measurement. So it can't be in the output up there, right? How do I know which one's endogenous and exogenous? We look at which one's on the left-hand side, right? So adjust must be the endogenous predictor because adjust is on the left-hand side. And then we can kind of see, just to interpret the regression. So for example, a 1 unit increase in risk leads to a 0.599 increase in adjustment. This is counterintuitive. A 1 unit increase in adjustment leads to 0.375 increase in achievement. And a 1 unit increase in risk leads to a 0.724 increase in achievement. So not all hypotheses are necessarily confirmed, right? So that's just a real world example of when that may not necessarily be the case. Any questions about the output here? We're almost done.
Like in a structural model, adjustment and achievement, they will become kind of dependent variables. Am I right?
Yeah, adjustment. Yes, these are dependent. Basically, they're dependent variables. Yeah, because these are endogenous. These are endogenous latent variables. Okay, because they're being predicted by something else. Good. Any other questions? Okay. Let's see if you don't mind answering. No, I think this one's too technical, the poll. All right, so we're going to conclude. Yay, finally. There's a lot more material that I put on the webpage. You can read that for yourself if you have time. All right, so this is the conclusion, okay? So this is like basically what we just learned. So SEM encompasses a broad range of linear models. There's linear regression, multivariate regression, path analysis, CFA for confirmatory factor analysis, and structural regression. These models are all parameterized rigorously in ListRel, okay? So this is a genius guy named Carl Jorskog invented this notation, but it's not like necessary for you to run the Lavaan syntax. And just know that Lavaan syntax is not ListRel notation. I only present ListRel notation because I want you to understand the nuances of SEM. So for example, a nuance of SEM, if you don't know ListRel, is that you don't know how to distinguish between an endogenous and exogenous variable. And you wouldn't know that, for example, in that you typically don't have an endogenous variable predicting another unless you have the B matrix. So gamma, for example, is the exogenous to endogenous relationship, and B is the endogenous to endogenous. You wouldn't know that unless you know ListRel syntax or notation. Why do you need to know? Because basically then you know that, you know, some things have residual variances and some things have exogenous variances, which you interpret differently. An exogenous variance is basically a variance of, let's say, risk, let's say, and then the residual variance is, let's say, of achievement, is what's the variance after accounting for risk. Okay, so you have to interpret those things differently, and the only way you know how to interpret that differently is if you know the difference between an exogenous and an endogenous variable. For the other thing you will know is that, you know, path analysis is a special case of multivariate regression. And how is that possible? Well, it's if you set the B to be 0, meaning I take away the relationships between endogenous variables, I basically have a multivariate regression. Okay, so basically what I'm saying is, what I've taught you today is basically how to identify these models in a very precise manner. Now, when you actually run Lavaan and you implement in your data analysis, you may not need to distinguish between all these variables. And that's really why ListRel has been modified over time, is that Lavaan has simplified the notation of ListRel so that, for example, it's all just Y variables. There's all endogenous variables. There's no exogenous variables. It's just called independent versus dependent variables. So every modification of ListRel, every program that exists today is a modification of ListRel. And that's why I start with ListRel as a teaching method. But now that you know ListRel, you can use it for your advantage and as you apply it into newer programs. Okay, and just to summarize, then SEM, okay? So SEM, when you have one outcome, SEM is an umbrella term for all these models we've talked about. So when you have one outcome and they're all observed, basically we have simple and multiple regression depending on how many exogenous variables we have. Now the fun part, because you already know the regression, the fun part, it really is when you have more than one outcome. You have 2 or more outcomes. You have 2 or more outcomes and they're all observed variables, and you only have exogenous to endogenous paths, and you have multivariate regression. If you allow the endogenous and variables to relate to each other, then you have a path analysis. Now, if you have two more outcomes and you have latent variables, you can either have a latent to observed variable, which is a factor analysis, or you can have a latent to latent variable, which is structural regression. And now you know every single model in this tree diagram. Okay. And then finally, I just have one last poll in terms of the content to see if, and thank you for staying to the end. I know it's like, it's a long seminar, so your brain's probably like fried by now, mine is. So thank you for staying to the end. But this is the last kind of summary poll, if you don't mind. So SEM encompasses a broad range of linear models and combines simultaneous linear equations with latent variable modeling. Multivariate regression means that there's always more than one exogenous predictor in my model. A variable being predicted is always endogenous. In structural regression models, the regression path only among latent variables. All right, I'm going to close the poll in about 5 seconds. And this is your last poll in 5, 4, 3, 2, and 1. I think you guys mostly get it. And I think I was tricking you, one of them. Okay, so SEM encompasses a broad range. You guys all got that. It's basically simultaneous linear equations with latent variables. That's what SEM is. Multivariate regression means that there's always more than one exogenous predictor. That's false, because multivariate regression, you can have one exogenous predictor, but it has to predict more than one endogenous outcome, right? A variable being predicted is always endogenous. That's not true, because exogenous indicators are considered exogenous, but it's being predicted by a latent factor. But that only exists in the context of a measurement model. And then this is a trick one, I think. Structural regression models, the regression path only among latent variables. What I was saying was the structural regression model that I was looking at, not in general, like SCM. But yes, structural regression models only allow regression paths to be among latent variables. And that's that gamma and beta path. Okay, so thank you for taking that. And that basically concludes the seminar. Now, if you don't mind filling out a brief survey to help me understand, what was good, what can be improved, and if you have suggestions for maybe future seminars, okay? So otherwise, thank you so much for coming, and I appreciate your time and hope you got something out of that.